Hello everyone, let's have a quick look at this question. Okay, here we go. A beam AB has a length of 4 meters, so it tells you from this there's 4 meters and a mass of 20 kg. The beam is suspended horizontally by 2 vertical tensions, so you got a tension here, okay, and you got the tension at D, which is holding it up. Right. The other rope is attached to the beam D. Yeah, there it is. So that's 0.7 from B, and that's 0.5 from A. The beam has been modeled as a non-uniform, very important, and the rod is lightly extensible. So it's non-uniform. I'm just going to assume that, let's just say there, the center of mass is there, and that's going to come down at 20 G, because that's the mass of this rod. Okay. It's given that the tension in the rope C is 3 times the tension at rope D. So let's just say the tension here is X. So the tension here is going to be 3X. Right? The tension at rope C is 3 times the tension at D. Okay. Determine the distance of the center of this mass from A. Okay, let's do that. So I'm going to call this distance from here to here, let's call that Y. Right, so first of all, let's solve this vertically. Horizontal, nothing's happening, but it's in equilibrium. So vertically, you got 3x plus the x, which is holding it up, and what's going against it is 20g. So that means 4x is equal to 20g, so x is equal to 5g. Right, so that means that's the tension in C is 15g, and the tension at D is 5g. Okay, that's holding up. So we're done with that. Find the distance. Right, okay, so what we now do, there's nothing else to solve here, so we have to go for the moment, and I'm going to take the moment at A. So if I go here and do the moment at A, you've got, right, this is pulling it up, so this is going to be moving it anti-clockwise. This is pulling it up, so this is moving it anti-clockwise, and this is going down in this motion with the force, and that's going clockwise. So anti-clockwise must equal clockwise as it's in equilibrium. So that means perpendicular length times wherever the direction of the force is, you take the perpendicular length to that and multiply them. So in here it's going to be 0.5 multiplied by the force pulling up is 15g, plus this is also going anti-clockwise, so from there to there, well, that's just 4 take away 0.7 is 3.3 multiplied by the force is 5g. Okay, so let's just quickly work that out. So we got 0.5 times 15 at 3.3 times 5, got 24g. Okay, so that's all the motion going anti-clockwise, which is going to be balanced with the clockwise motion. Let's just work out the clockwise motion. That's going to be going from there to there, so we don't know that length, which is going to be just y multiplied by 20g. That's the force going down perpendicular to that. Okay, so they're going to balance, so I'm going to write 24g is equal to 20 yg. Now they both got the g's on this, and we're just going to cancel that out. So you got 24 equals 20y, so divide through by 20, so y is going to be half that, 12 over 10, which is 1.2 meters. So that length from there to there, that distance there to there is 1.2, which is y. So the distance from this distance of the central mass to beam A is 1.2 meters. Done. Now, next one, a particle of mass m is now placed on the beam at the point where the magnitude of the moment of the particle's weight about c is 3.5 mass times gravity pull mg. Okay, so this mass, we know that from c, well actually if there's c, 3.5 is going to be right on the end here, because that's 0.5. okay, so this length from c all the way going there, the mass is going to be right on the edge here. So I know that there's the mass that's going down in the motion of mg. Okay, coming down. So that's where that mass is. Let's just do that in red actually, so it's different. So there's the mass right on the edge, because it's 3.5 meters from C. Okay, 3.5 from C. Okay, determine the largest value of m. Oh, it says here that the beam remains in equilibrium. Now, when we find out the largest possible value, we then say it's about to tip. Okay, when it's largest possible value, it's at tipping point. Tipping point means that it will start leaning down. Okay, start coming down. So that tipping point, when that happens, it then only has this kind of tension going upwards, and it loses tension here, it comes off there because it's balancing on here, just about to tilt at D. Okay, it's about to tilt there. So this will go. So mg, I'm going to put, so if we need to find the maximum, that's about to go. So mg, so if I take the moment at D, we've got that distance, which is 0.7 times mg. Okay, and that is about to tilt, so that's going to be nice. Trying to keep it, so in order to not just about to tilt but still keep in balance, that has to be less than or equal to this side. So that tension's gone, that's going to go in that motion, and that's going to match it. Now this time, since that's gone, it's going to be matching it in the weight of balancing from that motion. Okay, because it's leaning on these two, and that's going to be, let's see if that's 1 point from here. Take off 4, subtract 1.2 plus this distance here, 0.7, that's 1.9, so that's going to be 2.1. okay, going from there to there, from D, so that's going to be 2.1 multiplied by 20g. Because it's the point of tilting, we're not taking that now, that's about to go. But to stay in balance, m has to be less than that value, otherwise it will tilt totally, and then it no longer will be in equilibrium. So first of all, let's get rid of the g's. Let's just do 2.1 times 20, which is 42, and we've got 0.7 m. So m, largest possible value, is going to be less than or equal to, in order to remain in equilibrium, divide that by 0.7, and you get 60. So the mass has to be less than or equal to 60 to stay in equilibrium. If it's more than that, it will start tilting and start moving downwards. So maximum largest possible value n is going to be 60 kilograms. Okay.